In this chapter, we're going to talk about memory systems. So first, I'll introduce memory systems, and then we'll talk about memory system performance. And finally, we'll talk about what affects this performance and how we build memory systems, particularly caches and virtual memory. So a computer system's performance depends on both the processor performance and memory system. And here's a picture of the processor memory interface. We have the processor that sends the memory write signal, address, and write data to the memory, and the memory returns the read data to the processor. So in prior chapters, we assumed that we can access memory in one cycle, one processor clock cycle, but that really hasn't been true since the 1980s. So you can see this graph here with performance on the left shown in a log scale. So you can see the CPU or processor performance has grown, at a much higher rate than the memory system. And so then now there's what we call a memory gap, processor memory gap, so between the performance. So it takes many processor clock cycles to access memory. So this is the challenge, is to make memory appear as if it's as fast as the processor. And so in order to do this, we use a hierarchy of memory. Ideally, any given memory would be fast, cheap, and large, where cheap is inexpensive and not breaks easily. But so we want a fast, cheap, and large memory, but we can only really choose two. If we choose a fast and cheap memory, it's going to be really small. If we choose a cheap and large memory, it's going to be really slow. And so we use a hierarchy to act as if we have a fast, cheap, and large memory. And we build it from multiple types of memory. So here's a picture of the memory hierarchy. We have our CPU, our processor, and on chip, nearby that CPU, that processor, is the cache. And the cache is typically as fast as the processor, so it's one processor clock cycle to access. And then off chip, we have main memory, which is much slower, and even slower is the hard drive. And so here are some typical numbers. For example, SRAM, which is what cache is made of, costs $100 per gigabyte, but the access time is really fast, 0.2 to 3 nanoseconds. Whereas main memory, built from DRAM, is a lot less expensive, $3 per gigabyte, but a lot slower, 10 to 50 nanoseconds. And we can see that solid state drives or hard disk drives we're going to talk about this is what we use that for virtual memory, is a lot cheaper, 10 cents or to 3 cents, but a lot slower, 20,000 to 5 million nanoseconds. And so in order to make this hierarchy work, we have to exploit two types of what we call locality. The first one is temporal locality. This is locality in time. So if we use data recently, we're likely to use it again soon. So we exploit this by keeping recently accessed data in higher levels of memory, of the memory hierarchy, particularly the cache, for example. And so an example of this is, if you've used a book recently, for example, a textbook, likely use that again recently. Probably shouldn't go put it into your storage space back, over 5 miles away. And so if every time you have to go look at it, you have to go the 5 miles to get it. Instead, you want to keep it in your backpack, right? So you can keep it nearby to use. So that's an example of temporal locality. Spatial locality is locality in space. So if data was used recently, you're likely to use nearby data soon. So for example, if you're looking for a book in the library and it's by your favorite author, likely you're going to access the books nearby. Once you get to the stacks and find that book, you'll be like, oh, here's a new book I didn't realize that author came out with, and you'll grab both of them. So in processors, if data was used recently, likely the processor is going to use nearby data soon as well. So we exploit this by the processor, when it accesses the given data, it pulls in nearby data as well into the cache and keeps it there in the higher levels of the memory hierarchy.